3 loop where you have diagrams like this, and it may not agree with double scale string theory from this reasoning. So actually, we have done that calculation. It has not been published. It's not been published because it did not agree with double scale string theory. But at the moment, we're still trying to make sure that we're absolutely certain that we have not made any mistake in the 3 loop computation. But if that is the case, what we found is that at 3 loop, it did not agree with double scale string theory. So, but of course, in this story, the Yang-Mills amplitude, the 3 loop is the next order that has a chance of making sense. Because the 4 loop order, you know it cannot make sense. You have to complete this in some way that is yet unknown. But on the double scale string theory side, we have some completely well-defined answer, so we can just do standard string perturbation theory. I would summarize by saying that we know what the amplitude is at large distance on the Coulomb branch, and the question is to figure out how to interpolate toward the origin and try to kind of say something about learn something about the UV completion of the 60 gauge theory. And let me just make one more comment. People probably care more about the 2,0 version of the story than the 1,1, because there's this mystery of what is this low energy 2,0 superconformal theory. The computation from the double scale string theory point of view, from 2,0, is pretty much identical. The only difference is you have to relabel the little group indices, but actually expression for amplitude at string tree level is literally identical. Okay, so there, we do not have a non-abelian gauge theory description of the origin, but nonetheless, we can make the same statement about amplitude, at least at large distance, on the Coulomb branch of 2,0 theory. And it basically takes literally the same form as we have here. And one can try to then cook up some Coulomb branch abelian tensor effective theory to match on with these, and see what one can learn about the 2,0 theory from that. So I will end here. Thank you.
Any questions? So for the 2,0 theory, is there also BPS identification for the operator, like trace H to the?
Actually, yes.
So we would expect those to be exactly the same as the coefficient.
And in fact, in the recent work of Nixetti and I think a student, they actually have proved a non-realization result exactly of the same type I was hoping for here for the 2,0 theory. So and there, I think the statement is that the 60 term is protected, and nothing can be said about 80 or higher. So, yeah.
So there, the little string won't be computing those coefficients.
That's right. That's right.
So they're compatible down to some 4D.
That's another part of the story. So yeah.
So also in the integral, so we're expanding in a small mass limit or large?
So we are expanding in a large mass limit. It's expanding in the inverse of the mass. So it's not obvious that you have a well-defined expansion in that form. In fact, whenever so you might say if you go to higher loop order, you have UV divergence. Let's just take that divergent answer and try to expand and see what you get. But the problem is if you do that, you don't even get a well-defined 1/MW expansion. You don't get this kind of power series expansion. It doesn't start with 1/MW squared. So the expansion doesn't even make sense from that point of view.
So what I'm wondering is that the 3 loop computation, there's no UV divergence, but individual diagram, is there UV divergence in individual diagrams? The 3 loop.
I think there is, yeah.
So would there be an order of limit problem there that whether you first expand the large mass and
I don't think so, because you can just I don't think so.
Because okay.
Yeah, I think it's yeah.
It commutes.
Yeah.
Okay.
Yeah.
Any other questions? Okay, if not, thank you.
Okay.
This will be concluding our workshop. So thank everybody.